The main objective of sorting data is to keep our data in well-organized manner. By doing so, searching an element is quite easy. Bubble sort is one of the basic sorting techniques which is similar to selection sort. Let's consider the following example. I'll be taking an array of 5 elements with unsorted elements. You can see all the elements here are completely unsorted. This is the data before sorting. After sorting, you can see the output is in the array, the elements are ordered in ascending order. You can arrange them in descending order also, but as of this example is considered, I'm arranging elements in ascending order. Now we are going to see how bubble sort technique can be applied to arrange these elements in ascending order. Let's start. I've taken an array of 5 elements with completely unordered elements. Index position of this array started at 0 and ended at 4, and the total number of elements are 5. The bubble sort works with hint point adjacency. Adjacent elements are compared. For an example, at each iteration what I do is that I'll compare adjacent elements. 25 and 16 are compared. Since I'm arranging my array in ascending order, these two are not in ascending order. 16 comes here, 25 comes here. And then 25 is compared with 21. They both are not in ascending order. Swapping takes place. And it goes on. When we reach to an end of array, you can see that 25 will come here. In other words, the maximum of all these elements will definitely come here since you are arranging elements in ascending order. When we have done this thing, it means that our first iteration is completed. Repeat the same thing for rest of the elements. These 4 positions only. These 4 positions. Afterwards, we'll repeat the thing for 3 positions. And then we'll repeat for 2 positions. There we'll end up. Total number of iterations or passes that are required to complete this job is 4. The total number of passes has to be done. This job has to be done 4 times exactly. Since we have 5 number of elements, n-1 that is 4. 4 times we need to do this job so that we can arrange this completely unsorted data in ascending order. Let's do it. I started with the first iteration or the first pass. I'm comparing 25 with 16. They both are not in ascending order. Swapping takes place. After swapping, 16 and 25 are kept in their respective positions. Now I'll compare 25 and 21. You can see that the positions are incremented to 1 and 2. Before it was 0 and 1. Now it is index positions are 1 and so 25 is compared with 21. Both are not in ascending order. Swapping takes place. The positions are incremented. Now I'll be comparing the positions 2 and 3. That means values 25 is compared with 9. Both are not in ascending order. Swapping takes place. Afterwards, the positions will be incremented again. Now I am comparing position 3 and 4. That means value 25 is compared with 24. Both are not in ascending order. 25 will be kept in the last place. So after swapping, this is the endpoint. Further, there are no elements after position 4. We completed our first iteration. We need to do the same job repeatedly for the second iteration, third iteration, and so on. Up to n-1 number of times we have to do. At each iteration, you can see that how 25 came to this location. After second iteration, you can see that this position will be in green mark. This position will get its accurate place. Whenever I am doing the things for the second iteration from 16 to 24, I don't have to include this position. I don't have to repeat the logic for 25 because 25 have come and placed in its accurate place. There's no problem with 25 now. 25 is ordered. Now I'll completely concentrate on 16 to 24 only. These 4 positions only. Let's do it now. The same job is done. Don't have to worry. The same thing will be repeated again. We'll start again with starting positions 0 and 1. 16 is compared with 21. 16 is compared with 21. Both are in ascending order. Not a problem. Increment the positions. Now positions are 1 and 2. 21 is compared with 9. Both are not in ascending order. Swapping takes place. After swapping, again I'll increment the positions. 21 is compared with 24. That means position 2 is compared with position 3. Both are already in ascending order. No swapping is required. Here is the endpoint for the second iteration. We have completed 2 iterations now, meaning that the last 2 elements 24 and 25 are kept in their respective positions. Now we'll have to repeat the same thing or the same job for 16, 9 and 21. Another 2 iterations are required to finish our job. Let's do it. We again started with 0 and 1. 16 is compared with 9. Both are not in ascending order. Swapping takes place. Positions incremented by 1. Now positions are 1 and 2, values 16 and 21 are compared, both are in ascending order, no problem, swapping will not take place. This is an end of third iteration. After third iteration, you can see that 3 elements starting from position 2 to last position 4, all the values are arranged. So as to make you understand, these values are kept in green color. Now we'll repeat for the positions 0 and 1. This will be the last iteration, 9 and 16 will be compared. Fortunately, these 2 elements are already in ascending order, no swapping takes place, and the 16 is kept in its accurate place. Since we have only one element left over in the array, the element cannot be compared by itself. By default, we can end up this process. The total number of iterations that we have done are 4. Our job is done. This is what our expected output is. The logic is quite straightforward. You should have understood what kind of logic that we have done. With an example, the same logic is used for writing the program as well. We need 2 nested loops here. I loop, I'll call it as I loop and J loop. I loop is for maintaining the total number of iterations or passes. In our example, the total number of passes are 4, or total number of iterations I can say, those are 4. For each iteration, you should get inside and you should maintain a J loop to compare adjacent elements. Try to compare J element with J plus 1th element. If swapping depends upon whether you are arranging elements in ascending order or descending order. Swap these positions if required. That's it. You just repeat this process n-1 number of times. Automatically you can see the data in sorted order. This is the main logic to write the program. This is the parent loop, which stands for the total number of passes. It started from I equals to 0 to I less than n-1. Why n-1? Because the total number of iterations or passes that we need to repeatedly compare the adjacent elements is n-1 number of times. The total number of times are n-1. This is for the total number of passes. For at each pass or each iteration, I'll get inside, a child loop has to be maintained so as to compare the adjacent elements. For sake of child loop, I have taken a variable j, which is less than n-1 minus I. It's an obvious thing that j has to run only n-1 number of times, but you would wonder why minus I is taken into the account. Consider this example, which we have already done. In this example, 24 and 25 are already kept in their respective positions. They don't further require any kind of comparisons. To avoid comparing 24 and 25 again and again, minus I is taken into the account. At each iteration, exactly I number of values are already arranged. So it's always better to minus that unnecessary iterations. That is the reason why in the j condition we have written it as j less than n-1 minus I. If you don't do this minus I also, still the program executes perfectly for you. But if you avoid doing minus I, then unnecessary comparisons will be done. To make our program much more faster, this minus I is compulsory. Whenever these 2 conditions are true, then you will get inside, you will compare the adjacent elements. A of j is compared with A of j plus 1, which is the adjacent element. In case if left side element, that is A of j, if it is greater than A of j plus 1, that is its adjacent element, then swapping has to take place. Otherwise, swapping will not take place. Now let's look at the whole program and execute it. Now let's look at this program, bubblesort.c. I'll explain you this program line by line. I've taken an array of 10 elements and I've taken ij. I is for maintaining the total number of passes or iterations, and j is for the child loop to compare the adjacent elements. N is to store the number of values, temporary variable for swapping purpose. I'm asking user to enter n value within the range 10. Since I have taken an array of only 10 elements, within the range 10, user can give any value. That value will be kept in the variable n. And it depends upon the value that is given for n. I'll ask user to enter the %d number of values. That means n number of values. Instead of %d, the n value will be printed. So in my case, even though I have an array of 10, while executing this program, I'll prefer to give the number of values as 5. So I'll be entering only 5 values. Depends upon the n value, you'll be reading those values and you'll be keeping nicely into an array. And afterwards, so as to tell user what are the values that you have given, the unsorted elements, whatever the values that the user has given, I'm just printing those values. So before the actual logic is applied, because I wanted to show the output like, I wanted to print values before sorting the complete unsorted elements, the user input that has given. And after sorting, what are the output that we got, that I wanted to show it nicely. That is the reason why I'm printing the values before sorting. So before sorting what are the values that are there, you just display them, and afterwards here is the place where our logic starts. This is the main parent loop which is used to maintain the total number of passes or the iterations, and it runs up to n-1 number of times because the total number of passes in bubble sort is always n-1 number of times. At each pass you will get inside, since we have a chain loop which is used to compare adjacent elements, j starts always from 0, j should be less than n-1 and minus I. Why should we subtract I? Because at each iteration I number of values which are sorted and kept nicely at the last places, they don't have to be compared again and again. To avoid those unnecessary iterations, minus I is done. Whenever we are comparing a of j and a of j plus 1, if the condition is true, then I am swapping. To swap the positions of a of j and a of j plus 1, I have used a temporary variable temp. I am just keeping the first a of j value in temp, and then a of j plus 1, whatever the value, the next value is there, I am updating in the a of j. Since a of j previous value is already stored in temp, I am assigning that value in a of j plus 1. So it's a simple logic to swap to any two values using a temporary variable. Once if this approach is done, then finally I am printing the values. You can see that values after sorting, I am just printing the array. Here you will be seeing the final output. Since I haven't done any kind of compile time errors, compilation is successful. Let's execute. Enter number of values within range 10. My value is 5. Now I need to input 5 values, completely unordered inputs 16. You can see these are the values that I given: 15, 2, 14, 3, 16, completely unordered. I'm just displaying whatever the values that are there before sorting. This is my array: 15, 2, 14, 3, 16. Thereafterwards, my two for loops have executed, and wherever the swapping required, swapping is done, and our total number of iterations n-1, that means 5 iterations are done, and at each iteration depends upon the logic whatever we have seen so far, that logic has executed, and we got the final output as an ascending order: 2, 3, 14, 15, 16. So our approach is working. Think about timing complexity of bubble sort. To calculate timing complexity, we'll count only the loops that are used to do this job. So here are the main loops, two loops that are used, which are nested, that is used to finish our job. That is the reason why I have taken only loops into the account. The first loop runs n-1 number of times. For each iteration, j is also, at a worst case, it will run for n number of times. At a worst case, when I is 0, j is nothing but 0. It has to run, because since I is 0 here, it is also running n-1 number of times. So the worst case timing complexity, since I is running n number of times, and possibly for some value of I, j is also running n number of times, n into n, the worst case timing complexity is order of n square, where n is number of elements. We don't mind how many number of times we are swapping the elements, we don't mind about it, but the total number of times your j loop is executing, which depends upon I value, is the total number of worst case complexity is order of n square. And what about best case? According to sorting, best case means sorting the data which is already sorted, already ordered data. It could be some ascending order data or descending order data. There are some brilliant sorting algorithms, those who can find before sorting itself whether the data is sorted or not. But unfortunately, bubble sort is not that intelligent to identify the data whether it is sorted or not. So it is quite innocent, because it's a traditional and basic technique for sorting. It doesn't know whether the data is already sorted or not. Without knowing that fact, it applies the entire loops that we have written. It tries to compare adjacent elements, and n-1 number of iterations will run even for the sorted data. For all the cases, it means that including worst case and best case, for all the cases, the timing complexity is order of n square for bubble sort. There is one biggest advantage of bubble sort. It is the stable algorithm. It has one of the greatest feature of sorting algorithms called stability. How can I say the bubble sort is stable? For an example, when I have an input of unordered elements 72, 4, 12 and 4, there are two 4s in this particular array. To differentiate these two 4s, colors are maintained. This is pink color 4 and this is yellow color 4. Now when I apply bubble sort technique, I'll get my output like this. I'll get pink color 4 here and then yellow color 4 here and 12, 72. And when you can ask me, when you apply any kind of sorting technique, you might be seeing 4, 4, 12, 72, but you cannot always guarantee pink color 4 as the first 4 and yellow color 4 as the second 4. Only few algorithms will give you output like this. You could ask me again what matters because both are the same values. No, both are same values according to the values that you are seeing here, but according to the application. For an example, let us consider the student data. Two students can have same name. Let the name of the person be John. Two persons can have the same name John. It doesn't mean that they are always same in every category. Their physical appearance and their experiences and their professional skills may be entirely different. So for what reason we don't know, pink color 4 has appeared before yellow color. We should not violate this order of appearance. Pink color 4 is appearing before yellow color even after applying the sorting algorithm. Any algorithm which do not spoil this order of occurrences of same element even after applying the sorting algorithm. The sorting algorithm which preserves this order, that kind of sorting algorithm is called a stable algorithm. Fortunately, bubble sort is a stable algorithm. That's it. We are done.